Let's say learning approaches to dexterous manipulation.
Yes, we can see that.
Okay, great. Okay, hello everybody. I'm sorry I'm giving this talk remotely, but I hope you're all having a good conference. So my talk is about dexterous manipulation, and let's start with some examples. So, so these are examples of operations that one can do in a kitchen, and there's a wide variety here. Some of these involve tool use and so forth. But the important point that I want to make is that most of these would be very difficult to do with just a parallel jaw gripper. You really need a multi-fingered hand, and you very likely for many of them you might need tactile sensing as well. And the focus of my talk is really going to be about how to design controllers for solving these tasks. So we are not there yet, but I'll like to give you examples of what we can do today. So I want to start with this high-level view. So in my mind, there are broadly three families of approaches for acquiring skills. One is trial and error. Fancy way of saying that is reinforcement learning, then learning by watching videos, and finally learning by teleoperation. And I'll show you results from each of these techniques. And I think that in the future, we'll see a lot of combination of these techniques as well. So let's start with reinforcement learning. So reinforcement learning has high sample complexity, as we all know. So therefore, one has to work in simulation. I'm going to start with this paper, which is now more than a year and a half old, but it gives you an example of a task. So the task here is rotating this object about the z-axis. And what we are trying to show here is generalization, that it can work for many different objects. And that's shown here by the shapes of the objects are different, the sizes are different, weights are different. And yes, this technique works across quite a lot of range. And the technique was basically trained with reinforcement learning in simulation and then transfer. And here, as you can see, the rotation is about the z-axis. And the sensing here is just proprioception. So the question is, can we take this kind of technique and make it work in more complex situations? So this is a paper from last year. And here, what we are doing is considering the next level of this task. So the next level of this task is that we should have the ability to rotate about different axes. So in this slide, each row corresponds to different kinds of axes. So in that of rotation, and every column corresponds to a different object. So let's look at it. So the top row is rotation about the x-axis. The second row is rotation about the y-axis. The third row is rotation about the z-axis. I mean, this is the case you've already seen before. And then the final row is about arbitrarily chosen axes. So how do we achieve this? So it turns out that rotating about the z-axis, the first case that I showed, is actually the easier case. And these other axes are harder. And it turned out that to achieve this goal, we needed to first use better sensing. So the better sensing is what is shown here in this image. So what you have, you can see your typical RGBD camera there, Intel RealSense. But in addition, the fingertips. So the fingertips here are tactile sensors, and the image from that is shown on the, on the right. These are like some vision-based tactile sensor, and it gives you a much more delicate information about where the object is touching the fingers. So this is an Allegro hand. So the first key innovation is improve the sensing. The next point is how do we use this information? So I won't have time to get into all the details, but very important is that for the vision data, how we pre-process it. So we pre-process it by segmenting out the object and of course operating in the depth domain. So this reduces the gap for training from in simulation to working in the real world. And this observation has been made before. So this is the kind of policy that we have where we follow some of these principles which have been used a lot successfully in sim to real. One is using the idea of using privileged information at training time to develop a policy, and that at test time, what you need to do is to somehow estimate the conditions under which it has been under which you're operating, and the conditions here might refer to the shape of the object. So we have papers in the past on walking using rapid motor adaptation, which are in this paradigm. But here is the architecture for this particular approach. So the transformer provides enough context for capturing the context automatically. So here is the finding which I'm most excited by in a sense, and in a way, it's a lesson to carry over for other work. The lesson is, so here on the y-axis is the performance. So the performance for this task is how often can you keep rotating this object? How long? So the rotation reward, or how many rotations before the object falls down. And then what makes this challenging is obviously the fact that you just take some unknown object, pop it between the fingers, and you expect the policy to work. So the rightmost is when you have ground truth knowledge of the shape of the object, the shape, and so that's when the performance is best. On the extreme left is when you are just relying on proprioception. And the middle three columns correspond to the cases of having access to visual information from the RGBD camera, touch information from the fingertip sensors, or both. And if you look at the second to right column, that's the most exciting result, that if you have access to both vision and touch information, you get the best performance gain. And it's almost as good as having oracle knowledge. So this is one task, right? It's a task of in-finger rotation. But I think that this lesson will be found to be true in general. And this is, to me, like now I'm speaking like someone marketing work on tactile information. Tactile is something I believe in strongly, and I do not believe that dexterous manipulation at a large scale will ever be achieved without the use of both multi-fingered hands as well as tactile sensing. And here's a proof that using vision and touch together gives you better performance, and it's almost as good as having ground truth knowledge. So now I'll show you some work which builds on top of this policy. So imagine that you have a low-level policy which can rotate about any axis, and it keeps going. Now, you also need to know when to stop, right? Because you have an axis of rotation, and if I want to apply a finite rotation, meaning some rotation matrix to the object, then I need to know, I need to start, pick an axis, start rotating about it, but then you need to know when to stop. So what we do is one can try to do this task directly, and people have done that. But what we tried to do was to essentially learn how to stop. And that was by another policy which is on top of the low-level policy. And then here we'll show you some results. So here you're specifying that, let's say the goal here is rotate about the z-axis. So you specify the axis of rotation. So then it could be the previous paper. Just keep rotating. But here you have to know where to stop. And that's what you see here. And these lines that have been drawn on the object are mainly to make it easier for you to interpret whether it's doing the right thing. Okay, so this is rotating about the vertical axis, and this is very easy to interpret. And but we can also do these more difficult axes, which is the x-axis and the y-axis. And I'll show you these examples, and you can try to interpret if it is doing it correctly. At least I find this hard, and you have to sort of think and uh, do this. So this is a task which is, in my view, quite challenging for human observers. And my conjecture would be that it would be difficult to train this task using teleoperation. Okay. It really is a very challenging task where there's dynamics, you have to sense and you have to move. Okay. So I'll give you another example of a task from our group. This is work led by Torulin, where we are now not doing a task of rotation by one hand, but rotation about with using two hands. And the task is basically to twist the lid of a bottle. So so it's a bimanual task. So this is kind of delicate. It's basically you need to have both the hands need to synchronize, and you want to open different kinds of bottles. So let's use this word. So and again, the training is in simulation, and then the task culminates with with the bottle top falling off. And we trained in simulation, and we use vision as the sensor here. And this is really quite a hard problem, and we do not know of other work which can tackle this. But we are able to do this using the sim to real paradigm, and you can find uh, uh, result. I mean, the paper is on archive. One of the things that we learned here is that vision is important, and vision is challenging in these when the object is hidden in the hand. So in this work, we are not using tactile sensing. And further advances purely on the perception side of when an object is in the hand, how to do it. I mean, I think these will be important. And there's the hardware setup, and I won't go into more detail. Let's talk a bit about the second family of approaches, learning by watching videos. And this is a paper from like now 6 years ago, basically, which had one of the early demonstrations of this. So the idea is you have some YouTube video, and there are tons of YouTube videos, like 156 million hours of them. And this guy is doing cartwheels, and we want to make Atlas do cartwheels. So the Atlas is going to be in a physics simulator, and what we are doing is giving it a dense reward. So in every frame, the idea is to be as close to the human uh, pose as possible. And yeah, so anyway, so this is in the broad paradigm of imitation learning, which has been talked about a lot in child development. So because it's in a physics simulator, you have to deal, and you're doing it right, would require you to deal with the physics, right? And the Atlas has a slightly different morphology than the human. So that constraint has to be enforced at the time that you're training your policy. So here I'll show you our most recent work in this area. And here we are tackling the challenging problem of biped locomotion. And the paradigm that we are using is basically that learning a policy is like next token prediction with a transformer, very similar to what happens in language, but instead of a sequence of words, the sequence here corresponds to sensory motor tokens. So, and the data we can use from a variety of trajectories. So the data is raw trajectories. Trajectories can come from motion capture, they can come from internet videos, and then you train this transformer essentially with this task of next token prediction, and then we can deploy. Noteworthy is that when you have data where the trajectories are produced in simulation, then you have complete data. But when you have trajectories which you get from YouTube, then for some data might be missing. For example, the desired action is missing. So we can accommodate that in this paradigm by essentially having tokens corresponding to missing data. So we use all this variety of training data. So this is the interesting case that I wanted to draw attention to. So we have videos of, say, humans playing tennis, and then this motion can be transferred to a humanoid. Okay. And then now it becomes a trajectory to be used for training. And everything is sort of being thrown in. And we all know that neural networks can deal with variability and noise in the training data. It helps with generalization. And then this is the result. So here is a robot walking around in San Francisco, and we have more new results, which I don't have here, which are walking up and down on slopes and so on and so forth. Okay, next let's turn to solving this problem of imitation learning, but in the context of manipulation. So again, how do we get big data for robotics? One way of getting big data is if we could get YouTube videos or whatever, and then use that to train the robot. And now your big data problem is totally solved, right? Because you have 156 million hours of video on YouTube. And one way of going about it is to start by 3D-fication. So you 3D-fy the hand and you 3D-fy the object, and this will help solve the gap between the trajectory from your video stream and the trajectory to be used for the robot. So that's the goal shown here. So how do we solve this problem? We need to first solve the problem of 3D-fying the hand and then 3D-fying the object. So 3D-fying the hand is a classic problem. I mean, there are papers on this, like there's a famous Jim Ray and Takeo Kanade's paper from like 20 years ago. And people have been trying to do this, and it's hard because the hand, there's a lot of mutual self-occlusion, there's an object in the hand. And finally, we were able to build this model which does this very well. It was presented at CVPR, and you're free to download it and use it. And here are some videos. So the reconstruction is happening frame by frame, and it's in a variety of different settings. And already people are just downloading the software and using it. For example, the Stanford group of Chelsea Finn and et al., they've used this for, doing transferring of motion from a human to a humanoid, for example. So anyway, these examples show that it works in complex cases where the hands are interacting with different objects and so on. Okay, so we can solve the problem, and I think I feel very good about the solution. So this basically is a way to reconstruct hands, and even and it has quite a lot of generalization and robustness and dealing with occlusion from one hand to another and of objects in the hand. Then you need to be able to 3D-fy the object, and this is a paper which addresses that problem, and it builds on the machinery for 3D-fying the hand first, as well as the system called MCC, which was developed at Meta, published last year. So, so the way the architecture works is as follows. Okay, so suppose I want to reconstruct this hand object scenario with somebody manipulating a coffee mug as I have in my hand. So what first we do is reconstruct the hand, and the hand is represented as a point cloud. And then you try to reconstruct the cup in the context of the hand. So the hand defines a scale, right? Because if the fingers, my two fingers, my thumb and finger, they have a certain distance between them, and that gives you an idea of the scale of the cup. And so here the prediction is that of a point cloud, and then with that one can actually retrieve. And this technique, we can compare it to various other approaches that are out there. And then let me show you some results. So here are some just frames from videos. So this is just a single frame reconstruction. And now we have it in 3D hand, 3D object. And obviously this technique can be applied in video. So now you have trajectories. So let me show you some more results. So what's the dream here? I mean, I remember I started my talk with these examples of kitchen tasks, and some of which involve use of tools. And here the idea is we can take videos of humans doing that and then 3D-fy the hands, 3D-fy the objects, and then we have to find a way of using these trajectories for training robot policies. So now that's the next little segment of my talk, which is about hand-object interaction pre-training from videos. And so we can start with robot data. Now you can get 3D hand object trajectories. You can get this from a variety of sources. I mean, there are traditional mocap type techniques. There could be techniques like this lifting from videos. And this area will keep improving. I mean, we are not at the final point yet, but the technology is getting better every time. And then we use this for transferring and training robot policies. So the value, what's the benefit here? The benefit here is that you have huge amounts of video data. So this is much easier to get large data sets here than by collecting teleop trajectories, because collecting teleop trajectories takes time and effort, and maybe you need like 50 or 100 trajectories for doing a task. And here is some examples. And let me just turn to the demos. So you have a robot data set, then you train a general manipulation prior on the transformer. I mean, I showed you some examples with a biped locomotion. This is similar set of ideas. Some details which, I mean, we're going to put this paper out soon, maybe next week. And then there's downstream examples. So the benefits, okay, so you can just watch this video, and we can do this other popular approach as well, which is just collect teleops and then train a diffusion policy. But what you find is that with pre-training on video trajectories, the training becomes so much more easier and the resulting policy is so much smoother after downstream tuning. So you can rely on most of the work being done by the video trajectories, and then maybe like 5 examples where you do teleop, where you have complete state during the trajectory. So here's another example. So this is picking up a water bottle and fake pouring into this bowl. More examples. Okay, and then finally, I want to say that, of course, we can also learn by teleoperation. It's a challenging problem to set this up for multi-fingered hands, but we have done that in our group. And here are some examples to whet your appetite. Here you have a system, and I think this is Toru demonstrating sort of the control. And I'll just show you how some of these, learning collecting trajectories with teleop and then applying that. So this is a different hand, and so this is purely from teleop. Yeah, this is my last slide. So So this is an example where it would be difficult to do this with without if you're just doing a parallel jog repair, you could never pick up two bricks at one time. So I'll conclude here, and the grand message of my talk is multiple sources of sensing are important. Vision is important and touch is important. My second point is that there are three sources of training and developing policies. One is using reinforcement learning and simulation. The second one is learning from videos. And the third one is direct teleop. And these have varying sample complexity. They can be used in combination. But I think the future for this area is very bright. Thank you very much.
Thank you, Jitendra. We have time to take one questions. Okay, I think maybe I'll just propose trigger some discussions. So when we have some tasks, what do you think is what techniques should we use? So among the different techniques.
Yeah, so I think that there are some characteristics of these techniques which favor one or the other. So for example, when you're trying to do a very dynamic task which requires fast interaction between what is sensed and acted upon, then I think the task of rotating that object, I don't think that you could train that using teleop. That's a very fast dynamic task. Okay. So that's an example where you basically need to rely, you can't do it by teleop trajectories. What you really need is either simulation or this combination of sort of this learning from video, where simulation is perhaps the preferred method or some hybrid with learning from videos. When a task is very slow, like that stake transfer task, if you try to do it with RL, it just specifying the task becomes very challenging. Whereas specifying a task in a teleop framework is very easy. So I see that, like the task of upturning a steak in a pan. I mean, there the teleop type approach or the learning from video approach would seem to be more natural and preferable than learning with RL and simulation starting from nothing. You can, of course, do hybrids here, and I think that's what we'll find over time.